Hi everyone, Architecture and Operating Systems, and in this week we are going to discuss interconnections. Uh, what we did last week was discussing fetch execute cycles. I gave you a numerical example, how to add two numbers, and we learned what happens in fetch cycles, in reading instructions, and in executing and execute instructions, performing and implementing what we save on the memory as instructions. We start from the reading data to the last stage of performing all of them and use different registers, and we learn about all of the steps that should take place inside the machine to be able to do some operations. But now let's talk about what happens between different modules of computer. This figure, we discussed that in the first week of this series of CPU. And we discussed we've got different modules in computer structure, which is input, output, main memory, CPU. And they've got to talk to each other. So computer as a network of basic modules should be able to send and receive data, addresses, instruction, whatever between them. So we need to have interconnection structure. So what's that? It's a path for connecting the modules. We need to be able to send data from main memory to the CPU or instruction to the CPU, or when you enter data using a keyboard from input output device should be able to be located on the memory. So as you see, we need to be able to send and receive data, instructions, addresses, whatever between these modules. Also, between the ALU registers and control unit, we need to have internal bus or interconnection system. So this bus system, generally speaking, is a path for connecting the modules. The structure of this interconnection or interconnection structure depends on type of the exchange. Are we sending data? Are we looking for a specific address in the memory? They are different. Are we sending a signal, for example, from control unit to the ALU? As you see, we have different type of exchanges, and we need to know what they are, and then we've got to use a specific interconnection uh, structure for that. Let's discuss one by one because we have three main things: main memory, input, output, and CPU. Let's discuss memory first. So memory, as we discussed in fetch execute cycle, it consists of n words equal length. So from 0 till, for example, 1000, whatever. In IAS machine, we've got 1000 words. So we've got n words equal length. Each of them has got unique address. You remember in fetch execute, the program counter gives the address to the memory address register, and memory address register will go and take and find the address inside the memory. So it means that it should be addressable. So we need to be able to go and find the address. There you go. We need to go and find the data. So address is important to find the address in memory. So this is one type of exchange that we want. Data, read and write data. In our example last week, first of all, we read some data from the memory, and also at the end, we wrote data on the memory. So read and write of the data on memory, and finding the address as well. But reading or write, which one? We've got to send a signal. These arrows show the signals. Also, the output is, when you reading data, it means that the output of the memory is data. So the operation is indicated by read and write control signals. What happens? Do I need to write or read from the memory? So we need to send signals, but we've got to find the address. We need to write, should be able to write data on the memory, and also we should be able to read data from the memory. So the location for the operation is specified on an address. So these are the main type of exchanges that happens in memory: data, read and write on the memory, finding the address, specifying the address, and sending signal whether to write or read. So for the memory, we need these three type of exchanges. Input output module, similar to the memory, because we've got different ports, different interfaces that we have for a machine. For example, one is keyboard, one is monitor, one is a scanner, what is printer, different ports we have similar to the memory. This is addressable. If you want to send the file to the printer, use different port in your machine. So it's addressable as an output device. Similar to memory, internal point of view, if you want to send the data or read or write. So control more than one external device port unique addresses that we need to have. So if you want to send and receive the data, again, similar to the memory, we should have port. We need to have addresses for them, address. We should be able to read and write data. It's similar to the memory because we should be able to write on that and then read it from internal and external data, internal and external data. And also external data path input output with an external device if you want to send the data. Also, we should send a signal whether to write or read. Are we reading from the input device or we writing to an output device? So we should be able to say what to do. So we need to send and receive signal. So these two arrows shows the signal. We need to be able to find the addresses again based on the ports that I told you, and read data write data and read data from the memory. Also, we send an interrupt as well, interrupt signal. For example, you're writing a program or you're performing a program, but something happens, a priority comes up, and you need to stop that program and interrupt running that program and jump to another one. So input output device should send interrupt signal. Okay, now go to next program, stop this, go to next one. So we should be able to send signals as well. So here, as you see, we should be able to send signals, read and write and interrupt, sending data, sending and receiving data, data exchange type we need, and also addresses because we've got different ports. This is for input output device. The last one is the processor. The processor reading instruction and data. So we've got to get data here. Get data from the main memory or input output device or write on them. This is what we did in fetch execute. Receiving data, sending data. When you finish, you want to save it, you send the data to the memory. Use control signal to control the overall operation. CPU is a control unit, should be able to send signal. Control signals are sent. And also it receives interrupt signal. Something happens, the emergency comes up, or another program is running, you're interrupting by pressing some keys. So should be able to receive interrupt signals. And also we got some instructions. We should be able to read instructions from the memory. And in CPU, we should be able to go and find some addresses on the main memory. As you see, we have again 3 types of exchanges: addresses, data, and signals. So as you see, we have these 3 main types of exchanges between main modules that we have here. So interconnection structure must support the following types of transfer: memory to processor, memory to processor. The processor reads an instruction or a unit of data from memory. So it receives instruction, the CPU receives instruction and data from the memory. We discussed that in fetch execute. Processor to the memory writes a unit of data to the memory when you want to write write data or save data on the memory. Input output to the processor, input output to the processor. The processor reads data from input output device via an input output module. Again, we get the data from input output device and we want to actually present the data, send it to the output device, like printer, like a screen. Processor to input output device. In both ways, it works in both ways. As I said, the process sends the data to input output device. And at the end, input output to the main memory. There is a link between the main memory and input output device. Sometimes you enter the data, it goes and sits and writes on the main memory directly. So we should be able to actually have access to the memory directly here. So the interconnection structure that we want should be able to support all these types of transfers. So what is the interconnection structure? We have two types of interconnections. One of them is called bus interconnection that we will discuss it here, and the other one is point-to-point interconnection that I'll briefly go over that. First of all, bus interconnection. Bus interconnection actually um, a bus is a communication pathway connecting two or more devices. It's connecting two or more devices, so between the modules that we discussed. What is the key characteristics of that? It's a shared transmission medium. It's exactly similar to this bus. So many people can jump in, and in different points they can jump off. So this is exactly similar to our bus. This is shared. It means that data and instruction, all of them can sit on this bus and can go and use a single highway or road to uh, to go to a specific device. So that's a shared medium, like a highway. Highway is a shared for different cars. If you consider the cars as a unit of data, all of them are using the same highway, same bus. Address, signal, and data sit on this bus and go and uh, or deliver to the point that they've got to go. So that's a shared transmission medium. Multiple devices connect to the bus, and a signal transmitted by any one device is available for reception by all devices attached to the bus. This is similar to the bus network topology in the networks that we have. So it's a shared between them. It's a highway between all of these modules, and they can send and receive data using that shared medium. But there is a problem with that. If you send signals, because that's a shared medium, you might have signal overlap and become garbled. Only one device at a time can successfully transmit. If you have a shared um, medium between these modules, at one time only one device can use that. Otherwise, if two of them want to, because that's shared, if two modules want to send and receive data in the same time, there might be an accident between the signals, or we call it overlap or garble. So this is the disadvantage of bus that we have. What is bus? Bus consists of multiple communication pathways. We call them each lines. What is each line? Each transmits signals representing binary 0 or 1. We know that in the computer we use digital systems 0 and 1s. Each 0 and 1, each bit, is transmitted by a single line. Multiple of these lines together are called bus. For example, if you have 8 bits of data, if you want to transmit them, you need to have a bus with 8 lines. Yes, you can have bus with a less number of the lines, but if you want to send them simultaneously together, you need 8 lines to be able to send 8 bits of data. Bus system or system bus is called, all of these lines together are called a system bus. So when we say system bus here, it means that we have different lines between them, some of them for data, some of them for addresses, some of them for control signals. So all of them together are called system bus. So here at the beginning, we discussed different types of exchanges: data, read and write, for example, for this, signal, and addresses. Address, data for memory, signal for CPU, data, address, and signals. When we have all of these different types of exchanges, we need to have different types of buses. So we have three main types of buses. One of them is called data bus. When you have data lines together, we call them data bus. Address lines, when you have address together, we call it address bus. And control lines, the lines for control, sending the signals between different modules. We call them control bus. Data lines to provide a path for moving data among system modules. So this data line, as you see here, send and receive the data between input, output, memory, and CPU. It's called data line. Address line to designate the source or destination of the data on the data bus. So it says that the data bus, the address lines say that, okay, if you want to send this specific data, you need to go to a specific location. For example, 300 in our example in fetch execute. So address line should take that 300 and say, okay, this is the place that you need to go. And control line says that, okay, to control the access and use of the data on address lines, it controls the whole system and says, okay, you need to write on the memory on this specific address, this specific data. So it controls the whole thing. So as you see, we have three types of buses: data bus, address bus, and control bus. Data lines, as I said, are used for moving data. All the data lines together called data bus, as I said. And the width of the bus is the number of the lines. For example, if you have 8 lines of data, you can send at each time 8 bits of data. So it's very important in terms of the performance of your machine. For example, if you have 64 bits of instruction or data, whatever you want to send it, but you have only 32 bits of bits wide data bus. You've got only 32. So it means that you've got to send twice. First of all, send the first 32 bits, and in the second run, send the second part or the next rest of the bits, which is the 32 bits. So you need to use this shared medium twice. So there could be a potential risk of overlap between the signals and so many other things. So because of that, the performance of the machine will go down. So whenever you have higher number of the lines, you have a better and more efficient machine. So data bus width is a key factor in determining overall system performance. Address lines. We should be able to designate address. I showed you that for all of them, we need to be able to designate and specify the address. So address lines, what do? Source, destination of the data on the data bus. We need to see from which word we want to send on which port of the data, or where in which register we need to send the data. So all of them are addressable in the machine. So address lines does that, gives the address in bits. For example, if the processor wishes to read a word of a data from the memory, it puts the address of the desired word on the address line. If you want to read a word, you've got to say, okay, I want to read from this specific place. We did that in fetch execute. So we should be able to use these address lines. Bus width, address bus width determines the maximum possible memory capacity. So where do you want to send the data? It depends on the number of the lines that you have to be able to send the data. So the maximum number of the lines that you have for the address bus will tell you the maximum or the size of your memory. Because if you have, for example, 4 bits for address bus, it means that 2 to the power 4, you can have 2 to the power 4, which is 16 addressable location in the memory. So it means that your memory capacity should be 16. You cannot go for more than that. So it's very important, determines the address bus determines the maximum possible memory capacity. Also, address bus is important for input-output device. I told you about the ports. So, for example, we address in this way that we want to send it to the input-output device or the memory. The higher bits, the higher order bits, usually select the modules. For example, this one, the first one. If it is 0, it shows that the memory. If it is 1, it means that the ports for output or input. So 0, it goes to the memory where in this specific address. But if it is 1, it means that it should go to the input output device, which port, for example, port 0 here. So lower order bits, memory location, or the input output port here shows where to go, memory, the modules, memory or input output. The rest shows the address. This is the structure for address bus. And control lines control the access and use of the data and addresses. Why it's important? Because the data and address lines are shared by all components. This is the shared transmission. And someone should control that. Otherwise, you will have a garble. You will have accident between the signals. There must be a means of controlling their use. Because as a shared medium, someone should control that. Otherwise, the performance will go down. Control lines will do that. We've got two different types of controls. Control signals, the specified operation, command signals, which specifies the operation to be performed, reading, writing, whatever, interrupt, which address to go. You've got address bus, but where to exactly go to the which modules. And timing signal, which talks about the validity of the data and the information of the address that we have. We don't go in details of these two, but it's good to know the different types that we have. Control lines include memory, read, write, everything. Between all these devices, we need to have some control. So all of them is done by control lines. Between control lines include memory, write, read, input, output. So how does that happen? How we use this data bus? The buses. If one module wishes to send the data to another one, first of all, using the control signals, you need to obtain the use of the bus because that's shared. Okay, you want to send the data from memory to the CPU. First of all, you need to get enough lines for the data that you want to send. When you use the control signal to get that, then you transfer the data via the bus that you have. In the other way, if one module wishes to request data from another module, now you want to receive. Again, you need to get permission for using the bus and then transfer a request to other modules over the appropriate control and address lines. You get the permission for using the bus and then send the request to get the data. This is how bus works. This is bus interconnection, and the other one, which is quite contemporary, which is called point-to-point interconnection. This is being used these days. The point-to-point or contemporary systems are using them. Why? Because of the problem that buses have. Bus system have got a problem of overlapping signal, the shared medium. These are the problems with the bus, and the efficiency of the machine will be affected by that. So what's that? The new system, point-to-point, try to solve that. Using the bus, we've got latency because you've got to wait to get permission to use the bus. And it depends on the number of the lines. You've got to manage the lines and so many other issues. Point-to-point interconnection try to solve that. Why? To bring the latency down, to be able to send more data and the scalability, because you can add more cores. For example, this is the 4-core machine. So for scalability, you should be, if you want to add one more core, so to point, you can actually make a connection to that core to be able to send and receive the data and instruction and whatever. So it's good to have point-to-point interconnection, helps us for scalability. In 2008, Intel actually introduced this quick path interconnect, QPI, which is, as you see here, it's point-to-point connection between every pairs. You have connection between 2 by 2 of them. It's multiple direct connections. As you see, multiple direct connections. This is between each of them. It's layered protocol architecture. It means that there are some protocols on that, similar to the network that we have, for example, TCP/IP, that we get acknowledged when we send the data, and when it's received, we get acknowledgement for that. We've got some protocols there. Exactly the same structure happens here. So we've got layers of protocols, and we make sure that, for example, the data is delivered by the time and is quite quick and so on. And also the packets are data transfer. In the bus, we used lines for transmitting a single bit for each line. But here we use this similar to the network, we use packet. And we use packet size data transfer, and we use that concept to be able to send more data. So as you see here, QPI helps to increase the efficiency of the machine, because first of all, they are connected, different modules are connected directly to each other. There is no shared medium anymore. It's helped for scalability, and the data type is different. We are not sending the signal, we are sending the packets, and we've got protocols to, and we have more control on that, and it's way more efficient here, as you see. So this is the end of this lecture. Thank you very much, and see you later.